From the beginning of everything, to the grandest explosion ever witnessed, matter, antimatter, dark matter, and dark energy, all dancing together in a cosmic symphony. These elements slowly and steadily laid the foundation for creating our universe. According to the theory of expansion, as evident in our observable universe, it continues to grow even now. From the basic laws that govern everything to the tiniest particles that exist. Why were we brought into existence? Why does everything seem so perfectly designed? Are there other universes, or is this the ultimate prototype? Or could it be the creation of an intelligent being? Two factors hint at a plausible explanation. Firstly, the universe appears to be intricately balanced, with our existence as the living proof. Alternatively, our universe might not be specifically tuned for the emergence of life. It could just appear that way from our vantage point. Well, keep watching to find out. The universe isn't perfect. It simply exists. If we trace back to the very beginning, we can imagine that everything we see today once existed as a single point, a singularity. This marked the birth of space and time itself. From that point, the universe started to expand gradually, eventually giving rise to galaxies, stars, moons, and the life forms we know as humans. But how did we come into being? This question is perhaps the most profound one, seemingly beyond the realm of particle physics. To understand this, let's journey back about 13.8 billion years to the moment of the Big Bang. This cataclysmic event produced equal amounts of the matter that makes up you and me, and something called antimatter. Each particle has an almost identical antimatter counterpart, but with the opposite charge. When a particle meets its antiparticle, they annihilate each other, vanishing in a burst of light. The mystery lies in why the universe we observe today consists entirely of matter. If there had been an equal amount of antimatter, everything in the universe would have been destroyed. This points to a perplexing fact. The universe seems to have been fine-tuned for our existence. When we contemplate the universe, we don't usually picture it as a uniform expanse. After all, something as solid as our planet Earth is vastly different from the seemingly endless void of outer space. On a close scale, we encounter concentrated clumps of matter, objects like stars, planets, moons, asteroids, and humans. These clumps are separated by vast expanses of space, which also contain less dense concentrations of matter, such as interstellar gas, dust, and plasma. These materials are either the remnants of deceased stars or potential birthplaces for future stars. All of this is interconnected within our immense galaxy, the Milky Way. Zooming out to larger scales, galaxies can exist in solitude, known as field galaxies, gather in small groups like our local group, or cluster together in much larger numbers, sometimes numbering in the hundreds or thousands. If we examine even larger scales, we see that these clusters and groups are organized along gigantic filaments, some of which stretch across billions of light years in the cosmos. In the spaces between these filaments lie enormous voids, regions that are less dense, often devoid of galaxies and stars. However, as we expand our perspective even further, we discover that any given region of space resembles any other region of space. They share the same density, temperature, number of stars and galaxies, and types of galaxies. On the grandest scales imaginable, no part of our universe stands out as more or less special than any other part. Different regions of space exhibit the same general properties, no matter where we look. But our universe didn't originate with these large clumps and voids. When we examine the earliest snapshot of our universe, the cosmic microwave background, we find that the density of the young universe was uniform at every scale and in every direction. This uniformity means that the temperature was the same everywhere. First 3 Kelvin, then 2.7 Kelvin, then 2.73 Kelvin, and eventually stabilizing at 2.725 Kelvin. It was strikingly uniform throughout the entire cosmos. Imagine attempting to balance a pencil upright on the tip of your finger. It seems almost impossible, doesn't it? That's the kind of precision we're referring to when we talk about the fine-tuning of the universe. The fact that the universe's expansion rate and energy density are perfectly balanced is like discovering that the pencil on your fingertip remains steady without any effort. It's as if the universe itself is designed to support the existence of life. When we do encounter this unexpected kind of balance, we call it a system in unstable equilibrium. When we do find the proverbial pencil balanced in unstable equilibrium, we talk about there being a fine-tuning problem. Fine-tuning is an easy concept to understand in principle. For example, Big Bang models attribute an energy density, the amount of energy per cubic centimeter, to the initial state of the cosmos, as well as an initial rate of expansion of space itself. The subsequent evolution of the universe depends sensitively on the relation between this energy density and the rate of expansion. Pack the energy too densely, and the universe will eventually recontract into a big crunch. Spread it out too thin, and the universe will expand forever, with the matter diluting so rapidly that stars and galaxies cannot form. Between these two extremes lies a highly specialized history in which the universe never recontracts, and the rate of expansion eventually slows to zero. In the argot of cosmology, this special situation is called W equals 1. Cosmological observation reveals that the value of W for the visible universe at present is quite near to 1. This is, by itself, a surprising finding. But what's more, the original Big Bang models tell us that W equals 1 is an unstable equilibrium point. This is an example of cosmological fine-tuning. For the standard Big Bang model to yield a universe even vaguely like ours now, this particular initial condition had to be just right at the beginning. Some cosmologists balked at this idea. It might have been just luck that the solar system formed and life evolved on Earth. This habitable zone is also known as the Goldilocks zone, because planets orbiting at that just right distance from a star are not too hot or too cold to host liquid water. If planets are closer to their star, the water turns to steam. If they're farther, it freezes. Not only that, the fine-tuning of the universe that allowed it to be created played an immense role in the existence of life on Earth. Jupiter, for instance, plays a great role in the prevention of asteroids hitting the Earth and Venus's, protection from solar flares. But it seemed unacceptable for it to be just luck that the whole observable universe should have started so near the critical energy density required for there to be cosmic structure at all. If we come back to the expanding universe, that's the situation we find ourselves in. The universe appears to be enormously fine-tuned. On the one hand, we have the expansion rate that the universe had initially, close to the Big Bang. On the other hand, we have the total of all the forms of matter and energy that existed at that early time, including radiation, neutrinos, ordinary matter, dark matter, antimatter, and dark energy. Einstein's general theory of relativity gives us an intricate relationship between the expansion rate and the total of all the different forms of energy in it. If you know what your universe is made of and how quickly it starts expanding initially, you can predict how it will evolve with time, including what its fate will be. A universe with too much matter and energy for its expansion rate will recollapse in short order. A universe with too little will expand into oblivion before it's possible to even form atoms. Yet not only has our universe neither recollapsed nor failed to yield atoms, but even today, some 13.8 billion years after the Big Bang, those two sides of the equation appear to be perfectly in balance. If we extrapolate this back to a very early time, say 1 nanosecond after the hot Big Bang, we find that not only do these two sides have to balance, but they have to balance to extraordinary precision. The universe's initial expansion rate and the total of all the different forms of matter and energy in the universe not only need to balance, but they need to balance to more than 20 significant digits. It's like guessing the same number between 1 to 1 million as me 3 times in a row, and then predicting the outcome of 16 consecutive coin flips immediately afterwards. When we carefully examine even the tiniest particle, removing its basic laws and principles behind it and replacing it with your parameters, we'll find that even the smallest alteration would cause that particle to misbehave. Take, for instance, the universe constants that don't seemingly have a reason behind their value, unaffected by any physical forces. Think of these constants as the building blocks of the universe, much like the rules of a game. Imagine if changing the rules of chess even slightly resulted in a completely different game. Consider fundamental constants like the fine structure constant, alpha, roughly 1 over 137, which influences the strength of the electromagnetic force, governing how charged particles, like electrons, interact. If alpha were much larger, atoms would destabilize. Electrons would tightly bind to atomic nuclei, preventing complex molecules and disrupting the chemistry vital for life, star, planet, and galaxy formation. Now, contemplate the cosmological constant, lambda, linked to dark energy, driving the universe's accelerated expansion. At L's current tiny value of about 10 to the power minus 123, galaxies, stars, and atoms form. A significantly larger lambda would rapidly expand the universe, preventing complex structures and life. Conversely, if lambda were negative, the universe might have collapsed, halting its existence. Had the constants of nature taken slightly different values, we would not be here. The details of these sorts of calculations should be taken with a grain of salt. It might seem like a straightforward mathematical question to work out what the consequences of twiddling a constant of nature would be, but think of the tremendous intellectual effort that has had to go into figuring out the physical consequences of the actual values of these constants. No one could sit down and rigorously work out an entirely new physics in a weekend. And even granting the main conclusion that many of the most widespread structures of the universe and many of the more detailed physical networks that support living things depend sensitively on the values of these constants. What follows? Some physicists simply feel that the existence of stars and planets and life ought not to require so much luck. They would prefer a physical theory that yields the emergence of these structures as typical and robust phenomena, not hostage to a fortunate throw of the cosmic dice that set the values of the constants. Of course, the metaphor of a throw of the cosmic dice is unfortunate. If a constant of nature really is a fixed value, then it was not the product of any change process. It is not at all clear what it means to say in this context that the particular values that were obtained were improbable or unlikely. The way we perceive the universe today might be a result of a long-standing balance. However, in science, when we encounter a seemingly improbable coincidence, we don't simply accept it as an initial condition of our physical system. To do so would be to abandon the pursuit of scientific understanding. Instead, it's more scientifically sound to explore potential explanations for why such a coincidence might exist. One option, although not the most favored in my opinion, is to suggest that there are countless possible outcomes and countless universes in which these outcomes occur. We naturally can only exist in universes where our existence is possible, which is why our universe appears to have the properties we observe. While it's conceivable that the universe could have turned out differently, this approach doesn't offer a scientific solution to the mystery. Relying solely on anthropic reasoning could be seen as a scientific dead end. A strong scientific argument should do two things. Firstly, it should provide a mechanism for generating the observed conditions that seem finely tuned for us. Secondly, this mechanism should make additional testable predictions that differ from what we'd expect without it. This second condition is what separates a scientific argument from a non-scientific one. If all we can do is appeal to initial conditions, we lack a way to test the validity of our scenario. While other universes may exist, if we can't observe them and determine if they share the same initial conditions as our universe, there's no scientific substance there. On the other hand, if a prior phase of the universe set up these initial conditions while also making additional predictions, we'd have a significant scientific breakthrough. In the case of the universe's energy balance, where the expansion rate perfectly matches the total energy density, a theory like cosmic inflation is a strong candidate. Inflation could stretch the universe flat, aligning the energy density with the expansion rate. When inflation concluded, it would establish the initial conditions for the Big Bang. Importantly, inflation also generates additional predictions that can be experimentally or observationally tested, subjecting the theory to rigorous scientific scrutiny. When we encounter an unexplained phenomenon where two seemingly unrelated physical quantities match up exceptionally well, it's our duty to seek an explanation. While the outcome could be coincidental, we should only reach that conclusion if no other scientific explanation can be found. The key is to derive novel predictions that can be tested through experiments or observations. Without this, our theoretical attempts remain detached from reality. The fact that our universe exhibits such a remarkable balance between the expansion rate and energy density, both in the present and throughout its history, strongly suggests fine-tuning. With compelling predictions about properties like the spectrum, entropy, and temperature fluctuations arising from inflationary scenarios, confirmed by observations like the cosmic microwave background and the large-scale structure of the universe, we have a viable solution. Further testing will determine if our current best understanding truly provides the ultimate answer, but we must not dismiss the problem. The universe appears finely tuned, and our very existence serves as compelling evidence of this fact. Well, that's all for the video. If you enjoyed it, leave a like and subscribe to the channel, and I'll see you in the next one.